What is water pressure?
Pressure is the force divided by the area over which it is exerted. In 1647 the French scientist Blaise Pascal, 1623 to 1662, recognized that water exerts the same pressure in all directions. This statement is known as Pascal's principle. To understand Pascal's principle, think of a small cube of water as shown on page 96. The gray arrow in the middle is the force of gravity on the cube. As a result, the total downward force of the cube is larger than the upward force. Now, by Newton's third law, the outward force of the water is equal to the inward force on the water.
What are simple machines?
Simple machines are devices that match human capabilities to do work to tasks that need to be done. They can reduce the force required or reduce the distance or direction an object must be moved. Because we will eventually run out of fossil fuels, we need to explore other, more sustainable forms of energy, such as solar power. Suppose you want to lift a heavy object. If you use a machine, you will use your stored chemical energy to do work on the machine. The machine, in turn, does work on the object, which increases its energy. If the force is constant and in the direction of motion, then work is the product of force and distance moved, W equals Fd. The mechanical advantage, ma, of a simple machine is the output force divided by the input force, Foutput/Finput equals ma. To make the output force larger than the input force, you must choose a machine that has a mechanical advantage larger than 1. The drawing below illustrates the process. Note that you exert a small input force over a large distance. The machine exerts a larger output force over a smaller distance.
What distinguishes objects that sink from those that float?
An object will sink if the downward forces on it are larger than the upward forces. There are two downward forces: the force of the liquid above the object and its weight, the force of gravity. The upward force is the force of the liquid below it. Let's think of a cubic object of height h and area of the top and bottom a. Its volume, V, is then given by V equals Ha. Density is the mass divided by the volume, or P equals m/V. Let's start by considering the difference in water pressure between the bottom and top of this cube. Pressure is force divided by area, so, using L bottom equals top plus water GH. We can write F bottom slash A equals phi top slash A plus water GH, so F bottom equals phi top plus water caret Ha. Now we recall that Ha is the volume of the cube and water Ha is therefore the mass of the water. Water, whose place is taken by the cube of matter. The net downward force on the object in the water is then the force on the top plus the object's weight less the force on the bottom. That means Fnet equals phi top plus mobject, bottom from the results of the paragraph above. Fnet equals mobject, mwaterg. Therefore, if the object's mass is larger than the mass of the water whose place it takes, it sinks. If the mass is smaller, then it will rise. Weight is the mass times the gravitational field strength, g, so the net force is Fnet equals wobject, waiter. The water whose place the object takes is normally referred to as the water displaced by the object.
How can you reduce the bending of a beam bridge?
The simplest way to keep the roadbed from bending is to use a king post. In the illustration below, the downward force of the center of the bridge pulls down on the vertical post. This places the diagonal braces under compression. They transmit the force to the piers. The upward force on the post makes the net force on the post zero. It is under tension. While the king post bridge can reduce the bending in the center of the bridge, it can do nothing about bending between the pier and the bridge center. One solution is to add a second vertical post and connect the two by a horizontal member, creating a queen post bridge. But a method that allows much more support on a longer bridge is the truss. Similar methods of translating downward forces to compression forces exerted on the piers on the ends of the bridge were known to the Romans who worked in stone and concrete. They were famous for the arches used in their massive aqueducts. One such aqueduct, the Pont du Gard, was completed in 18 BCE and was used to carry water a length of 270 meters. 886 feet, over the Garden River Valley in southern France. Cables suspending or holding up the roadbed are draped over a set of tall vertical towers called pylons. The pylons support the suspension cables from which vertical cables are attached that lift the deck. The ends of the suspension cables must be anchored into the ground at each end of the bridge to exert the tension forces on the cables. The first known suspension bridge was constructed in the 7th century CE by Mayans at their capital Ixtlan, Mexico. It spanned 100 meters.
What does sustainable energy mean?
The amount of fossil fuels is limited. There have been major advances in discovering oil and extracting more from existing reservoirs, as well as recent advances in obtaining natural gas and oil from shale. But these sources, as well as coal and uranium, are not being replaced. Sustainable energy sources, primarily wind, water, and solar energy, ultimately receive their energy from the sun, and therefore will be available for billions of years. The present use of these sources is minimal. There are many difficulties in increasing their use. Wind power is highly variable. Water energy from traditional dams and reservoirs causes environmental problems. Energy from waves and tides has yet to be developed widely. Solar energy can be directly converted to electricity using photovoltaic cells. But these cells, at least at present, are inefficient and costly. Large solar farms exist, at which solar energy heats a fluid so it can boil water to use with steam turbines driving electrical generators. An additional problem in increasing the use of many of these sources is that they require the use of very rare materials, which are both costly and not easily obtained. Nevertheless, recent analyses suggest that a combination of nuclear, wind, water, and solar energy could replace most of the use of coal and oil for electric energy production.
What major discovery did Archimedes make in the 3rd century BCE and how did he apply it?
Archimedes, c. 287 c. 212 BCE, lived in the city of Syracuse on the island of Sicily, then part of Greece. He was charged by the king of Sicily to find out if his crown was made out of pure gold or an alloy of gold and silver. Archimedes had to do this without destroying the crown. One day, when bathing in the public baths, he noticed that when he stepped into the bath the water rose. He had seen this many times before. But this time he recognized that this common occurrence could help him solve his problem. Legend has it that he was so excited that he ran naked through the streets of Syracuse, shouting "Eureka!" or "I have found the answer." He then did experiments where he hung the crown on one end of a balance and a piece of first gold and then silver from on the other end. When the weight of the crown and that of the metal were equal, the balance was horizontal. He then immersed the balance in water. If the crown and the metal had different volumes, the water they displaced would be different and the balance would tip. He found that the balance tipped when both the silver and gold pieces were on the balance. Archimedes had found that the crown was not pure gold, but a mixture of silver and gold. The king had been cheated. Archimedes had discovered a principle of hydrostatics, liquids at rest, that would one day carry his name. Archimedes' principle states that an object immersed in a fluid will experience a buoyant force equal to the weight of the displaced fluid. A huge steel ship like an aircraft carrier can float instead of sink like a stone, because it can displace enough water to compensate for its weight and because the air inside of the ship makes its density actually less than the water around it.
What challenges are there in building skyscrapers?
The first challenge is to design a foundation that can support the tremendous weight of a large building. The best way is to dig down to the bedrock. This can be as close as about 21 meters, 70 feet. In New York City to almost 61 meters, 200 feet, in Chicago. If the distance is short, holes can be bored and concrete piers can be formed in the holes. More frequently a caisson is required. This is a large hollow waterproof structure that is sunk through the mud. Pulling it into and then out of the top of the caisson. A third method is go build a large steel and concrete underground pad that floats on the top of a hard clay layer. The load that the foundation must support includes the weight of the building, its furnishings and equipment, and the changing load of occupants. In addition to the loads, strong winds must also be considered. The walls of early tall buildings were constructed of masonry that supported the weight of the building. The 16-story 65.5-meter, 215-foot, high Monadnock building in Chicago, built from 1889 to 1891, required 1.8-meter, 6-foot, thick walls at the base. It was so heavy that it sank, requiring steps to be constructed between the sidewalk and the ground floor. The second half of the building used a steel frame on which masonry was attached, allowing much wider windows to be used. The steel frames can be bolted, riveted, or welded together. When the 59-story, 279-met 915-foot, tall Citigroup building was constructed in New York City from 1974 to 1977, the frame was bolted together. But later computer models showed that if hurricane-strength winds struck the building, it would be in danger of collapse. As a hurricane moved up the eastern seaboard in 1978, workers hurriedly welded plates over the bolted joints. Luckily the hurricane moved out to sea, sparing New York. Another effect of winds on tall buildings is to make them sway back and forth. While a variety of braces can reduce the sway, they add weight to the building. Another method is now used. The Citigroup building has a 400-ton concrete damper at the top. The damper moves back and forth, opposing the wind-driven motion of the building and reducing sway. Dampers, both liquid and solid, are used in tall buildings. Towers, offshore oil drilling platforms, bridges, and skywalks. The 210-meter, 690-foot, Burj Al Arab Hotel in Dubai has 11 mass dampers. The dampers can also mitigate the effect of earthquakes. Transporting large numbers of people into and out of upper floors is a challenge too. Those who design the elevator systems, as was demonstrated in the collapse of the World Trade Center buildings on September 11, 2001, stairways can be used in emergency situations. But the simultaneous movement of occupants down and firefighters up the stairways caused severe problems. Another consideration is the safety of occupants in case of fire. Some buildings have entire floors designed to be especially fire-resistant, so that people could gather there and be safer than on other floors.
What are the sources and uses of energy in the United States?
The tables below explain how much energy the United States uses per source and where the energy is used. The United States used 99.2 quads of energy in 2009, where each quad equals 1,000 billion BTUs. Electrical generation, 39.97 quads, is very inefficient. Only 31.5% of the energy from the source, coal, natural gas, oil, nuclear, is transformed into electrical energy. The transportation industry is also wasteful in terms of energy. With 75% of the energy, mostly petroleum, it uses being wasted as heat.
What was the first type of bridge?
The first type of bridge ever used was a beam bridge. This bridge was probably just a fallen tree that was used to cross a ravine or a small stream. The tree was probably supported by the riverbed or by a group of rocks. Beam bridges consist of a horizontal roadbed supported by vertical piers on the shores that are planted in the ground. Beam bridges are limited by the resistance of the roadbed to bending.
Are machines with mechanical advantage equal to one useful?
They are because they change the direction the force is exerted, which often makes it easier for the person to exert that force.
What is an inclined plane?
A ramp is an example of an inclined plane. Instead of lifting an object to the height at the end of the ramp, you move it a much longer distance on the surface of the ramp, but it requires much less force. So, the ramp has a larger output force than an input force, it has a mechanical advantage greater than 1. That is, ma equals foutput slash finput equals, length of ramp, slash, height of ramp. According to the Americans with Disabilities Act, a wheelchair ramp should have a maximum increase in height of 1 for every 12 length of the ramp. The Act says that the maximum rise should be 2 minus a half, so the ramp must be 30 long. The input work is finput XL, where L is the length of the ramp. The output work is foutput XD, where D is the rise and foutput is the weight of the person plus wheelchair. If there is no sliding or rolling friction, then finput XL equals foutput XD. The mechanical advantage is L/D. So finput equals foutput slash ma, and the force needed to push a wheelchair up the ramp is given by finput equals foutput slash L/D. If the weight of the person plus the wheelchair is 200 pounds, then the force needed to push the person up the ramp is finput equals 200 pounds slash 3072.5, equals 17 pounds. Look at the cutting edge of a scissors. It's an inclined plane where the input is the force and motion of the closing blades and the output is the outward movement of the paper after it is cut.
What is the buoyant force?
From the equation obtained in the answer to the last question, you can see that when you place an object in water, its weight is reduced by the weight of the water displaced. The reduction in weight, object, waiter. That is the net upward force of the water, is called the buoyant force.
What are some typical power outputs?
The following table was adapted from Wikipedia's entry on orders of magnitude, power. Retrieved on November 13, 2009. Unit example *femto-watt, 10 to 15 watt, 10 FW, approximate lower limit of power. Reception of digital cell phones picowatt, 10 to 12 watt, 1 PW, average power consumption of a human cell microwatt. 10 to 6 watt, 1 carat W, approximate consumption of a quartz wristwatch milliwatt, 10 to 3 watt. 5 to 10 MW, laser in a DVD player watt 20 to 40 W, approximate power consumption of the human brain. 70 to 100 W, approximate basal metabolic rate used by the human body. 5 to 253 W, per capita average power. Use of the world in 2001 500 W, power output of a person working hard physically. 909 W, peak output power of a healthy human. Non-athlete, during a 30-second cycle sprint kilowatt, 103 watts, I. 366 kilowatts, power received from the Sun at Earth's orbit by 1 square meter up to 2 kilowatts, approximate short-time power output of sprinting professional cyclists. 1 kilowatt to 2 kilowatts, rate of heat output of a domestic electric tea kettle. 2. 4 kilowatts, average power consumption per person in the United States as of 2009. 40 kilowatts to 200 kilowatts, approximate. Range of power output of typical automobiles megawatt, 106 watts, 1.5 MW, peak power output of a wind turbine. 2.5 MW, peak power output of a blue whale. 3 MW, mechanical power output of a diesel locomotive. 16 MW, rate at which a typical gasoline pump transfers chemical energy to a vehicle. 140 MW, average power consumption of a Boeing 747 jumbo jet. 200 to 500 MW, electrical power output of a typical nuclear power plant. Gigawatt 109 watts, 2.074 GW, peak power generation of Hoover Dam. 4.116 GW, installed capacity. The world's largest coal-fired power plant. 18.3 GW, current electrical power generation of China's Three Gorges Dam. The world's largest hydroelectric power plant. Terawatt, 1012 watts. 3.34 TW, Average total power consumption of the United States in 2005 50 to 200 TW, rate of heat energy release by a hurricane petawatt. 1015 watts, 4 PW, estimated total heat flux transported by Earth's atmosphere and ocean away from the equator. Towards the poles 174.0 PW, total power received by Earth from the Sun Yottawatt, 1024 watts, 384.
How can a machine with a mechanical advantage less than or equal to 1 be useful?
If a simple machine has a mechanical advantage less than 1, then you exert a larger force on it than it puts on whatever object it contacts. The output force is less than the input force.
What is the tallest structure ever built?
Structures and towers are listed separately from skyscrapers. The Warsaw Radio Tower on the outskirts of Warsaw, Poland, was the tallest structure ever built. Although it needed to be supported by long cables to keep it up. The tower reached 646 meters, 2,119 feet, into the sky. Unfortunately, in August 1991, the tower came crashing down during repair work. The tallest structure ever built that is still in existence is the KTHI-TV Tower in North Dakota, which stands with the help of cables 629 meters, 2,063 feet, tall. The tallest self-supporting tower in the world is the Canadian CN Tower, whose tip is 553 meters, 1,815 feet, above the city of Toronto.
What happens to a balloon when it is submerged in water?
When an air-filled balloon is placed underwater, the water, which has higher pressure than the air, exerts a force on all sides of the balloon. The pressure from the water causes the air to compress inside the balloon. The deeper the balloon is taken into the water, the greater the pressure, and therefore, the smaller the balloon will become. The pressure from the water will compress the balloon until the air pressure within the balloon can supply an equal amount of force against the water.
Why does a small clump of steel sink, while a 50,000-ton steel ship can float?
In order to remain afloat, a ship needs to displace an amount of fluid equal to its own weight. Therefore, if a clump of steel is placed in water, it will sink because it is much denser than water and its volume isn't large enough to displace a weight of water equal to its own weight. A 50,000-ton steel ship can easily stay afloat because it can displace 50,000 tons of water. That is because its hull isn't all steel, but contains a large amount of air. Therefore its density, its mass divided by its volume, is less than that of water.
Why do closed containers sometimes dent or even collapse on cool days?
Just as a balloon can become smaller when placed under water. A sealed container can change its shape and even collapse under certain atmospheric conditions. For example, a container that stores gasoline for a lawnmower is usually sealed when it's not being used. If the container were sealed on a warm day, when there was little atmospheric pressure. Subsequently on a cool, high-pressure day, the gasoline container could be crushed. A second reason is that gasoline vapor exists in the tank. And at low temperatures more of the vapor condenses to liquid, reducing the pressure of the gases in the tank.
What is the tallest building in the world?
The tallest building, until recently, was the Sears Tower, now the Willis Tower. In Chicago, Illinois, which was built in 1974 and is 443 meters, 1,453 feet, high. 3 new skyscrapers in Asia now surpass this height. The Petronas Towers in Malaysia, completed in 1996, are 452 meters, 1,483 feet, high. The Shanghai World Finance Center in China, completed in 2008, stands 492 meters. 1,614 feet, high, almost half a kilometer into the sky. The Burj Dubai, Dubai Tower, 818 meters, 2,684 feet, high, the world's highest, opened in January 2010.
Why does a stone sink but wood float?
A stone is more dense than water. That is, if you compare the mass of a stone to the mass of the same volume of water, the stone's mass will be greater. Therefore its weight will also be greater, so a stone, weighter will be positive. And there will be a downward net force. Therefore the stone will move downward through the water until it rests on the bottom. Wood, on the other hand, is less dense than water. If the wood is pushed under water, weighter will be negative. There will be an upward force on the wood and it will rise.
What type of simple machine is a screw?
You can think of a screw as an inclined plane wrapped around an axle. The ancient Greeks used a screw to lift water. Screws and bolts are also used to fasten two pieces of wood, plastic, or metal together. Screws have a large mechanical advantage, and thus the distance the screw thread moves. in its circular motion is much larger than the distance the screw moves into the material. Therefore the force the screw or bolt exerts to hold the material together is large in comparison to the torque used to turn the screw. Screws and bolts are also inefficient machines because of the friction between the screw and material, or between the metal of the bolt and nut.
What is a fluid?
Solids retain their shape because strong forces hold the atoms in their places. In a liquid the forces keep the atoms close together, but they are free to move. In a gas the atoms are about 10 times further apart than in either solids or liquids, and forces between them are very weak. As a result of weaker forces, a liquid or gas can flow freely and assume the shape of their container. They are called fluids. There are two main areas of fluid study. The field that studies fluids in a state of rest is called static fluids, and the field that analyzes the movement of fluids is called fluid dynamics. We will first explore static fluids.
What are the types of simple machines?
There are four major groups of simple machines: levers, including wheels and axles; pulleys, including gears, and the inclined plane, including wedges and screws.
Why is a stone easier to lift when it is in water?
Even though the stone sinks because it is denser than water, there is still a buoyant force on it given by Uchtone, waiter, so the stone's weight is reduced. Floating usually refers to a liquid such as water, but can anything float in a gas? Remember that there is a difference in pressure of any fluid between the bottom and top of an object in it given by L bottom equals top plus pGh. Even though the density of a gas, P, is much smaller than that of a liquid, there is still a pressure difference, and therefore a buoyancy. There is another difference between a liquid and a gas. A gas can be compressed, and so the density of the atmosphere decreases as you rise. When a hot air balloon is launched, the air within it is heated and it will rise. As it rises, the density of the air decreases, and so the buoyant force decreases. At some height the weight of the balloon and basket equals the weight of the air displaced, and the balloon stops rising. The operator of the balloon can go higher by making the gas in the balloon hotter, and thus less dense.
Where is the longest bridge in the United States?
The longest bridge in the United States, a US Pension Bridge, ranks as the sixth longest bridge in the world. The Verrazano Narrows Bridge is between Staten Island and Brooklyn, New York. This bridge, completed in 1964, spans 1,298 meters, 4,260 feet. The span between the towers of the Mackinac Bridge that links the upper and lower peninsulas of Michigan at 1,158 meters. 3,800 feet, is shorter than that of the Verrazano Narrows Bridge. But when measured by the distance between the cable anchorages, it is the longest bridge in the Western Hemisphere. The length of the entire bridge, shore to shore, is 5 miles.
Why is a wedge like an inclined plane?
A knife is one example of a wedge. Look carefully at the sharp edge of a kitchen knife. It looks like two inclined planes put back to back. As the knife blade moves down through food, the wedge pushes the pieces apart. A hatchet or axe is another example of a wedge. Wedges are also used to split wood. In this case, the flat end of an axe is often used to drive the wedge into the end of a log, which is then forced apart. Wedges are inefficient machines because there is usually a large amount of friction between the wedge and the material, which leads to increased temperature of both the material and wedge, and thus heat transfer.
What are the limitations on simple machines?
Simple machines must, like everything else, obey the law of conservation of energy. That means that the work done on the machine equals the work the machine does plus the heat the machine puts out because friction has increased its thermal energy. Some machines are highly efficient, meaning input and output work are almost the same, while others put out only a fraction of the work put in. The drawing on page 74 shows a simple machine where the machine has warmed up. That means its thermal energy has increased. It is now hotter than its surroundings, so it transmits heat to its surroundings, which are not shown on this diagram. The output work of the machine is smaller than the work put into it. That means that for the same input force, the output force is reduced by an inefficient machine.
How far will it rise?
As some of the wood rises above the level of the water, the volume and the mass, and therefore the weight, of the water displaced will be reduced. When the weight of the wood and the weight of the water displaced are equal, the net force on the wood will be zero and it will no longer move.
What is the difference between a dead load and a live load?
In order to remain static, bridges, and all structures, for that matter, must be able to withstand loads placed on them. A load is simply the engineering term for force. Dead load is the weight of the bridge or structure itself. The live load, on the other hand, is the weight and forces applied to the bridge. As a result of the vehicles and people that move across the bridge at any one time. Of course, in order to be safe, engineers account for much higher live loads than would normally occur.
What exerts this force?
If the cube is at the edge of the container, then the container exerts the force. You can check that for yourself. Use an empty fluid container, say a juice box or milk carton. Punch a hole in one side. Pour water into the container. To keep the water from leaving through the hole, you have to exert a force with your thumb. The same would be true if the hole were in the bottom.
If the air pressure is 101,300 newtons per square meter, why don't we get crushed?
Since our bodies have air inside them. The air inside our bodies is at the same atmospheric pressure as the air outside our bodies. Therefore, the pressures are equal and we can move quite freely in our atmospheric environment. The remainder of our body is mostly liquid water and cannot be compressed. The same cannot be said for divers. As the divers go deeper and deeper, the water pressure increases. At a depth of 10 meters, 32 feet, it is about twice atmospheric pressure. A diver can breathe in compressed gas to balance this pressure.
How can that be useful?
It's because the distance moved, output distance, is larger than what you move, input distance. And, therefore, the output speed is also greater. A baseball bat, tennis racket, and golf club can be considered simple machines in which high speed of the end of the implement is desired.
What is the newest hybrid of bridges?
One of the newest, prettiest, and most economical bridges is the cable-stayed suspension bridge. With its sleek lines and thin roadways, it is the perfect bridge for most mid-span designs. The Tatara Bridge, in Onamiki, Japan, completed in 1999, is the longest cable-stayed bridge in the world, with a span of 890 meters, 2,919 feet. Cable-stayed bridges suspend the roadbed by attaching multiple cables directly to the deck supporting the roadbed. These cables are then passed through a set of tall vertical towers and attached to abutments on the ground. Such engineering methods reduce the need for heavy expensive steel and the massive anchorages that are needed to support suspension bridges.
What exerts the downward force on the top of the cube?
If the cube is not at the top surface, then the force is exerted by water above it. If it is on the top, then air pressure, which we will discuss shortly, exerts this force. Because the downward force exerted by the fluid is greater than the upward force, the force, and hence the pressure, increases as the depth of the fluid increases. So the pressure at the bottom of a container of fluid is greater than at the top. The amount of increase in pressure is given by the product of the density P, the gravitation field strength G, and the depth H, or pGh. That is, the pressure on the bottom, L bottom equals top plus pGh.
What happens to the buoyancy of the ship when cargo and passengers are added?
When cargo and passengers are added to a ship, its weight increases. As the ship's weight increases, it sinks further into the water, displacing a greater weight of water. If it sinks so far that water can spill into the ship, increasing its weight even more, the ship sinks to the bottom of the water. The amount the ship sinks in the water as a result of cargo and passengers can be critical for navigation and maneuverability. Large cargo and cruise ships have numbers on the bow of the ship that indicate how far the distance is between the water line and the bottom of the ship. This distance is called the ship's draft. If the ship has a 6 km, 20 foot, draft and the water is only 5.5 km, 18 feet, deep, cargo and passengers must be unloaded to allow the ship to rise.
What happens to the buoyancy of the ship when cargo and passengers are added?
When cargo and passengers are added to a ship, its weight increases. As the ship's weight increases, it sinks further into the water, displacing a greater weight of water. If it sinks so far that water can spill into the ship, increasing its weight even more, the ship sinks to the bottom of the water. The amount the ship sinks in the water as a result of cargo and passengers can be critical for navigation and maneuverability. Large cargo and cruise ships have numbers on the bow of the ship that indicate how far the distance is between the water line and the bottom of the ship. This distance is called the ship's draft. If the ship has a 6 km, 20 foot, draft and the water is only 5.5 km, 18 feet, deep, cargo and passengers must be unloaded to allow the ship to rise.
How much water does a ship need in order to float?
Not a lot of water is needed to keep a ship afloat. Just enough so that it can displace enough water to equal its weight. Therefore, if a ship were to enter a canal that was just a bit larger than the size of the ship's hull, it would float as long as there was a small film of water around the entire hull of the ship.
How much water does a ship need in order to float?
Not a lot of water is needed to keep a ship afloat. Just enough so that it can displace enough water to equal its weight. Therefore, if a ship were to enter a canal that was just a bit larger than the size of the ship's hull, it would float as long as there was a small film of water around the entire hull of the ship.
How do blimps remain at a chosen altitude?
A blimp is a non-rigid airship that floats in the air solely. Due to the buoyant gas within the giant balloon-like bag, it typically carries over 5,000 cubic meters of helium at a density about 7 times less than air. An airship floats in the air in the same manner as a ship floating in water. The weight of the airship must equal the buoyant force of the gas inside the bag. In order to increase the altitude of the blimp, the pilot increases its buoyancy by adding gas from pressurized tanks to the blimp, which expands the flotation bladders, displacing the heavier air and increasing the buoyant force until the reduced weight of the blimp equals the reduced weight of the air. To lower the airship, the buoyancy is decreased by releasing gas from the flotation bladders, which then decrease in size, displacing less of the heavier air. Because helium is a safer gas than hydrogen, it is what is used in today's blimps.
How do blimps remain at a chosen altitude?
A blimp is a non-rigid airship that floats in the air solely. Due to the buoyant gas within the giant balloon-like bag, it typically carries over 5,000 cubic meters of helium at a density about 7 times less than air. An airship floats in the air in the same manner as a ship floating in water. The weight of the airship must equal the buoyant force of the gas inside the bag. In order to increase the altitude of the blimp, the pilot increases its buoyancy by adding gas from pressurized tanks to the blimp, which expands the flotation bladders, displacing the heavier air and increasing the buoyant force until the reduced weight of the blimp equals the reduced weight of the air. To lower the airship, the buoyancy is decreased by releasing gas from the flotation bladders, which then decrease in size, displacing less of the heavier air. Because helium is a safer gas than hydrogen, it is what is used in today's blimps.
Why is helium used inside airships instead of hydrogen? Isn't hydrogen more buoyant?
although hydrogen is twice as buoyant as helium, and would be more effective in lifting an airship off the ground, hydrogen gas is extremely dangerous. The German airship, or Zeppelin, the Hindenburg, the world's largest airship at the time, was destroyed on May 6, 1937, in Lakehurst, New Jersey, when it exploded into a huge fireball while attempting to land. 36 people died in the explosion. In 1937, the United States was about the only source of helium in the world, mostly from one gas well in Texas. The Nazis wanted to buy helium for their Zeppelins, but the United States refused to sell it to them as it was considered a strategic resource. Helium is formed from the radioactive decay of uranium and thorium in rocks. It is used today to cool devices and make them superconductive. As a result, the amount of helium available is rapidly decreasing.
Why is helium used inside airships instead of hydrogen? Isn't hydrogen more buoyant?
Although hydrogen is twice as buoyant as helium, and would be more effective in lifting an airship off the ground, hydrogen gas is extremely dangerous. The German airship, or Zeppelin, the Hindenburg, the world's largest airship at the time, was destroyed on May 6, 1937, in Lakehurst, New Jersey, when it exploded into a huge fireball while attempting to land. 36 people died in the explosion. In 1937, the United States was about the only source of helium in the world, mostly from one gas well in Texas. The Nazis wanted to buy helium for their Zeppelins, but the United States refused to sell it to them as it was considered a strategic resource. Helium is formed from the radioactive decay of uranium and thorium in rocks. It is used today to cool devices and make them superconductive. As a result, the amount of helium available is rapidly decreasing.
What are airships used for?
Since the first airship flight in 1852, by Henry Giffard in France, the dirigible, or airship, was used predominantly for military purposes. In the First and Second World Wars, airships were used for bombing and surveillance on both sides of the Atlantic. Commercial passenger transportation on airships was conducted for only a few years, while today's blimps are used for advertising and for televising sporting events from high elevations.
What are airships used for?
Since the first airship flight in 1852, by Henry Giffard in France, the dirigible, or airship, was used predominantly for military purposes. In the First and Second World Wars, airships were used for bombing and surveillance on both sides of the Atlantic. Commercial passenger transportation on airships was conducted for only a few years. While today's blimps are used for advertising and for televising sporting events from high elevations.
What happens to the helium balloon that a child releases?
If the balloon is tied tightly, the balloon will expand as its altitude increases. This expansion is caused by the lower atmospheric pressure at higher altitudes. Eventually, the helium's volume increases so much that the rubber balloon breaks, releasing the helium.
What happens to the helium balloon that a child releases?
If the balloon is tied tightly, the balloon will expand as its altitude increases. This expansion is caused by the lower atmospheric pressure at higher altitudes. Eventually, the helium's volume increases so much that the rubber balloon breaks, releasing the helium.
What is fluid dynamics?
Fluid dynamics is the study of fluids in motion.
What is fluid dynamics?
Fluid dynamics is the study of fluids in motion.
What is hydraulics?
Hydraulics deals with the use of liquid in motion, usually in a device such as a machine. Oil is the most common liquid used in pumps, lifts, and shock absorbers.
What is hydraulics?
Hydraulics deals with the use of liquid in motion, usually in a device such as a machine. Oil is the most common liquid used in pumps, lifts, and shock absorbers.
How does a hydraulic lift work?
Pascal's principle states that pressure in a liquid is independent of direction. Pressure is force divided by area, so force exerted by a liquid is equal to the pressure times the area. A hydraulic lift has a small piston in a cylinder. If you exert a force on the piston, it will create a pressure in the fluid. The lift also has a second, large area cylinder and piston. The fluid creates a pressure in the cylinder that exerts a much larger force on the piston because of its larger area. Therefore, the lift has a mechanical advantage. Of course, energy is still conserved, so the small piston must move much farther than the large piston. An automobile lift, used in many automotive repair shops. Allows the operator to use very little force to lift an automobile off the ground. By pushing liquid from a small diameter cylinder and piston through a thin tube that expands into a larger diameter cylinder and piston, which is located beneath the vehicle to be lifted. Since the liquid cannot be compressed like air, the liquid from the small cylinder is pushed into the large cylinder, forcing the large piston to move upward.
How does a hydraulic lift work?
Pascal's principle states that pressure in a liquid is independent of direction. Pressure is force divided by area, so force exerted by a liquid is equal to the pressure times the area. A hydraulic lift has a small piston in a cylinder. If you exert a force on the piston, it will create a pressure in the fluid. The lift also has a second, large area cylinder and piston. The fluid creates a pressure in the cylinder that exerts a much larger force on the piston because of its larger area. Therefore, the lift has a mechanical advantage. Of course, energy is still conserved, so the small piston must move much farther than the large piston. An automobile lift, used in many automotive repair shops. Allows the operator to use very little force to lift an automobile off the ground. By pushing liquid from a small diameter cylinder and piston through a thin tube that expands into a larger diameter cylinder and piston, which is located beneath the vehicle to be lifted. Since the liquid cannot be compressed like air, the liquid from the small cylinder is pushed into the large cylinder, forcing the large piston to move upward.
What are some other places where hydraulic lifts are used?
Besides their valuable use in auto repair shops, hydraulic lifts are used in elevating crane and backhoe arms, adjusting flaps on airplanes, and applying brakes in automobiles. It is the non-compressible characteristics of liquids that make hydraulic devices so useful. Oil is used rather than water because it does not freeze. This heavy crane boom uses hydraulics to lift the boom.
What are some other places where hydraulic lifts are used?
Besides their valuable use in auto repair shops, hydraulic lifts are used in elevating crane and backhoe arms, adjusting flaps on airplanes, and applying brakes in automobiles. It is the non-compressible characteristics of liquids that make hydraulic devices so useful. Oil is used rather than water because it does not freeze. This heavy crane boom uses hydraulics to lift the boom.
What is pneumatics?
Whereas hydraulics uses liquids to achieve mechanical advantage, pneumatics uses compressed gas. Since gases can be compressed and stored under pressure, releasing compressed air can provide large forces and torque for machines such as pneumatic drills, hammers, wrenches, and jackhammers.
What is pneumatics?
Whereas hydraulics uses liquids to achieve mechanical advantage, pneumatics uses compressed gas. Since gases can be compressed and stored under pressure, releasing compressed air can provide large forces and torque for machines such as pneumatic drills, hammers, wrenches, and jackhammers.
In what ways do fluids move?
When fluids move slowly, they exhibit steady or laminar flow. When the speed increases, the flow becomes turbulent. In some cases, laminar flow is desired, in others, turbulent flow is better.
In what ways do fluids move?
When fluids move slowly, they exhibit steady or laminar flow. When the speed increases, the flow becomes turbulent. In some cases, laminar flow is desired, in others, turbulent flow is better.
Why do your ears hurt when you dive to the bottom of a swimming pool?
Just as the weight of the air above us creates atmospheric pressure, the weight of water creates liquid pressure. Close to the surface of a pool, there is very little water that can push down and increase water pressure. The further a person dives below the surface, however, the greater the water pressure. The eardrums are especially sensitive to the increased pressure, for they do not have the reinforcement that the diver's skin has. In fact, your eardrums can usually feel pressure when diving just 1.5 to 3 meters, 5 to 10 feet, below the surface of the water. Feet, deep or in the ocean at a depth of 10 meters, 32 feet. Although the ocean contains a lot more water than a lake, it is the depth that determines the weight of water directly over a diver that defines the amount of pressure the diver experiences. Therefore, a diver who is 20 meters below the surface of a lake will experience more pressure. In fact, twice the pressure than the ocean diver experiences at 10 meters. Salt water is denser than fresh water, but the increase in pressure caused by the increased density is small in comparison to that caused by the difference in depth.
Are other muscles and bones in your body so easily characterized?
Most are not, because tendons that transmit the force from The muscle to the bone are long and go through several bends. Consider sports equipment like baseball bats, tennis rackets, and golf clubs. They are often used as extensions of your arms. So the person plus the bat or club has to be examined together. But note that in every case the SYSTEM is a third-class lever. Where a large distance moved, and therefore greater speed, is favored over an increased force.
How does a hydraulic lift work?
Pascal's principle states that pressure in a liquid is independent of direction. Pressure is force divided by area, so force exerted by a liquid is equal to the pressure times the area. A hydraulic lift has a small piston in a cylinder. If you exert a force on the piston, it will create a pressure in the fluid. The lift also has a second, large area cylinder and piston. The fluid creates a pressure in the cylinder that exerts a much larger force on the piston because of its larger area. Therefore the lift has a mechanical advantage. Of course, energy is still conserved, so the small piston must move much farther than the large piston. An automobile lift, used in many automotive repair shops, allows the operator to use very little force to lift an automobile off the ground. By pushing liquid from a small diameter cylinder and piston through a thin tube that expands into a larger diameter cylinder and piston, which is located beneath the vehicle to be lifted. Since the liquid cannot be compressed like air, the liquid from the small cylinder is pushed into the large cylinder, forcing the large piston to move upward.
What is a lever?
A lever is a bar that rotates around a fulcrum or pivot. The locations where the input and output forces are exerted relative to the location of the pivot determines the class of the lever. As shown on page 76. The width of the arrows illustrates the force while the length shows the distance moved.
How efficient are levers?
The only place where friction can occur with a lever is at the pivot point. So, as long as friction is minimal there, the lever can approach 100% efficiency.
Where does the bicep muscle attach?
The attachment is close to the elbow, so the forearm is a third-class lever.
Where would you put the material to be cut if more force is needed to make the cut?
You would put it nearer the pivot. On the other hand, if the material is easily cut, Cutting near the tip of the blades provides enough force and speeds up the cutting.
How is atmospheric pressure measured?
A device to measure gas pressure is called a barometer. There are two major types of barometers, the mercury barometer and the aneroid barometer. Galileo's secretary, Evangelista Torricelli, 1606–1647, the unit of pressure. The Tor, was named after him, developed the mercury barometer in 1643. It consists of a thin glass tube about 80 centimeters, 31 inches, long, which is closed at the top. Filled with liquid mercury and placed upside down in another mercury-filled dish. Depending upon the atmospheric pressure pushing on the mercury in the dish, the level of mercury in the tube will rise or fall because there is no air above it. By measuring the height of the mercury, which would usually be between 737 and 775 millimeters, 29 to 30.5 inches, high, atmospheric pressure of the atmosphere can be measured. The most common household barometer is the aneroid barometer, in which atmospheric pressure bends the elastic top of an extremely low-pressure drum. By measuring the amount the top bends, a measurement of atmospheric pressure can be determined. The aneroid barometer is often used in airplane altimeters to measure altitude. Since atmospheric pressure decreases as altitude increases, the aneroid barometer is an ideal instrument to use. It is much safer than the mercury barometer. Because mercury vapor is poisonous and the mercury must be exposed to the atmosphere,